Hello, everyone. My name is Hamid Azimi, and I'm part of the TechnologyCatalogue.com team, and I'll be your host for today's webinar. With me are Babak Moradi, representing Leap Energy, as well as Wesley Emery, representing iRPM. And we are joined by our expert host, Dave Masson, for the Q&A section. Before getting to the presentations themselves, I would like to raise 3 points. Number one, please bear with me during this presentation, as the execution might not be so smooth. As you know, due to coronavirus outbreak, I'm here in the office by myself, so I don't have the assistance that I usually get. So my apologies ahead of time. The second point I wanted to raise out is your ability to be able to ask questions, your ability to access these technologies through the TechnologyCatalogue.com. As you can see, you can access the TechnologyCatalogue.com, and within the module Subsurface, you could basically access the technology within the submodule of Reservoir Modeling. The third point that I wanted to raise out is the ability for our audience to ask questions during this webinar. There is the chat functionality on the right-hand side that you could access and ask your questions, and our presenters will make sure to answer those questions at the end of their presentations. Having said that, without any further ado, I will hand it over to Babak for his presentation part. Babak, to you.
Hi, good morning, everybody. My name is Babak Moradi, based on the KL from Leap Energy. My background is petroleum engineering. By the way, I'm doing the programming, and during last few years, I worked as a data scientist in the oil and gas industry. Today, I'm going to talk about one of our new technology, call it the Poseidon reservoir management tools for a mature oil field. Maybe first we can see a short video on the Poseidon. After that, I can go through our slides.
Welcome to Poseidon demo video. Today, we would like to show you the key aspects of that innovative reservoir management suite. The full cycle workflow in Poseidon covers 5 main steps, including data scan, production allocation, analytics, remaining oil, and prediction. Data scan. In this module, you can find more than 70 validators to screen new datasets for mistakes and integrity issues. Data scan will find missing or wrong production data, well events, unphysical behavior, and other erratic elements of the dataset. Identified issues could be quickly assessed using plots, as well as quickly corrected using embedded tools and changes propagation. Production allocation. Allocation module would allow you to conduct commingling analysis and perform vertical production allocation using deterministic single-phase and a stochastic multi-phase model. It generates multiple solution sets in alignment with surveillance data if available. Analytics. Poseidon Analytics includes a wide set of features helping engineers to develop a better reservoir understanding. Analytics cover many classical methods like material balance and decline curve analysis, as well as modern predictive techniques. Remaining oil. Remaining oil is one of the amazing Poseidon features based on smart predictive methods of saturation propagation. It produces a dynamic saturation maps with non-simulation approach and automate history matching on a single run. You could also visualize movable oil on the map to find new infill locations. Prediction. Poseidon allows you to conduct different types of predictions, from simple DCA or type curve methods for just historical wells to advanced neural network and remaining oil integrated forecast for the new wells. Currently, we are showing you a high-level neural network training process to predict new wells by learning from historical wells' performance. Thank you for your attention. More information about Poseidon you can find in our website, poseidon.services. Please kindly contact us in case of any inquiries.
Okay, actually, currently, more than 70% of the global oil is producing from the mature oil field. And there is a last chance to discover a new giant oil field. That's why the mature oil field is quite important, especially the identifying the bypass oil is the key element to unlock the remaining potential of the mature oil field. Here in the upright side figure of this slide, you can see actually the 3D models or numerical simulator is a precise tool to study of the mature field. But it's quite time consuming or resource consuming. By advancement of the new technology, we can reduce the running time of the numerical simulator, but we need more resources. That's why in the x-axis I put time and resources. In the another hand, we have some simple model like MBAR or material balance or bubble maps or analytic method. They are quite fast and they need less resources, but of course less accurate. In the lab, we try to introduce the new technology, call it the Poseidon. Fast technology, but still accurate. Here, that's why we are in the somewhere on the top of this plot, and you can see much faster compared to the simulator. Actually, Poseidon is a modular software. It includes 5 different modules. You can run this module independent or all connected together, and you can run it as a full cycle, depend to the user actually. And here we have a data scanning, allocation, analytics, ROCM, and prediction. During next few slides, I will explain each module individually. The first module is data scanning. Actually, at this module, we have more than 70 validators to identify and quantify the missing data or recognizing the unphysical trends, or easily we can recognize inconsistency between your production data and perforation data, or if you have a sudden change, for example, in the water cut. One of the examples has been shown in the bottom figure. For example, here we have a sudden change in the water cut. And the software can recognize this sudden change automatically. And user has 3 options here actually. And the software can fix this issue automatically, or we have a second option, the software or user can fix it manually, or as a third option, the user can leave the data as it is. But always we suggest to fix this issue because the Poseidon is a data-driven software and the accuracy of data is important and it can increase the performance of the software. Besides of that, the Poseidon can produce some heat maps for you. Actually, these heat maps help to the user to identify which wells or which area of the reservoir has a more issue and allow to focus on the critical wells or group of the wells. The second module is zonal allocation. Actually, some reservoir in the North Sea or in Asia Pacific, they are producing as a commingle, and always we have an issue of the zonal allocation. When we want to do the layer-wise study, we need to know how much we are producing from each layer. Actually, this module helps you to solve this issue. In this module, actually, we have some pre-allocation analysis, or we call it the commingle analysis in the Bottom left side, you can see some figure. For example, we provide the user some information about the coming-getting or trivial production at the field level and the layer levels. And after that, we can run the allocation process. In our allocation module, we support some command method like KH or KHP. But the issue with these two methods is the water cut for different layers is the same. Also, the water breakthrough time will be the same for all layers. That's why in the LEAP, we developed a new method called the advanced allocation. At this method, actually, we try to construct some water cut type here for each layer. And we try to run some search optimizer, obtain the flow rate for each layer based on the water cut type here, and sum up the rates and compare it to the wear rate. And we try to minimize this objective function. And during this process, we can obtain multiple solutions. This can be one of the advantages for advanced allocation. And if you have a PLT data, you can decrease the number of the solution. Or also we have some method to decrease the number of the solution. And the good thing here is instead of having one solution, you can have a multiple realization. And later on, you can use this solution in your LTRO study, and you can cover the uncertainty range due to the allocation issue. Here at the bottom, you can see one of our field examples. We compared the KH allocation with the advanced allocation. For example, at the zone 9, you can see the KH allocation tell us the recovery factor is around 98% for that zone. It's quite unphysical and unrealistic. But our advanced allocation produced around 97% of oil, and recovery factor is make more sense compared to the 98%. Okay. Our next module is analytics. Actually, analytics can act as an X-ray for your reservoir. Easily, you can find some valuable information from your historical data. We have a different function in our analytics. For example, we can compare 4D seismic data versus production data. We can produce some attribute for you. You can run the multi-tank ball in the Poseidon. We can produce the bubble maps for you, or we can plot the creaming curves, for example, initial oil rate or EUR of each well versus well count or a date. Also, another module is a predictive analytics. This module is quite interesting. Actually, during this module, we prepare a lake of data for machine learning. One of the difficult jobs for running the machine learning is preparing the input data. This module helps you to prepare your data set to run the machine learning. Another module is well interaction. Actually, during this module, we look at the production data of each well, and we try to find some relation between the different wells. And by this way, you can find some connectivity between the wells, and sometimes you can recognize the fault or some channel inside the reservoir only by looking at your production data. Beside of those modules, we have a value of the injection. Easily you can find the value of the water injection or gas injection by analytic tools. We have a DCA or decline curve analysis. In our DCA, we have some command method and some manual method, and you can run the hyperbolic, for example, exponential or harmonic. Also, we have some automated method. and the software can do run the DCA for all the wells automatically, and it can run it at the well level, well layer level, or at the field level, and it can produce some summary table for you. For example, if you want to do the reservoir study or run the NFA, and if you have too many wells, this module can be quite helpful, especially if you run it automatically. And at the end, we have a well type curves. The software can create some type curves for you. And in the general, when we are talking about the mature fields, we have a history of the production data. Normally, we have several wells. It means we have too many production data. That's why this module can be quite helpful to recognize some pattern in your reservoir, and in the short time frame and cost effective, you can get some result by using these different methods. Another module we call it the remaining oil component mapping, or ROCM. Our remaining oil component mapping, or ROCM, actually is similar to the simulator. Our input is the same. Also, the output almost is the same. We produce the saturation map, mode map, or different map that normally a simulator is producing. And it's quite useful for LTRO study, actually. At this module, we convert the production data to the saturation log. Actually, you can see some of the produced log by Poseidon at the bottom of the screen. As a first step, we convert our historical production data to this saturation log. We can calculate the average water saturation at the well level, and the software try to use some stochastic method and produce some saturation surface to match this average water saturation at the well level, and the total of the oil at the field level should be consistent with the material balance, actually. But sometimes matching the material balance and the saturation at the well level is not possible, and we report it as an error. In the software, we have an option to monitor the error. And here, during creating our saturation map, we can consider the geological model. For example, we can consider the fault or channel area. For example, when we have a channel area, we move the water faster, or when we have a fault, our algorithm can recognize it and we stop the water at the fault. Okay. Here is an example of the Poseidon application at one of the fields in the Middle East. Actually, we use the allocation, or I can call it, actually we use the data scanning, or allocation, data analytics, and LTRO and prediction for this field. First, we done the allocation. After that, we come to the LTRO. In the LTRO, one of the uncertainty was allocation. Also, we had the uncertainty in the contact level. We had some uncertainty in the PVT data, and reservoir pressure, and also some uncertainty about the fault. We introduced some base case. After that, for each uncertain parameter, we run one low case and a high case. We plot the tornado plot, actually, and we find the important parameters. When we find the important parameters, we try to combine all the parameters, and we construct several cases with a different combination of the parameters. and we run it through our LTRO engine. The advantage of our method is that quite fast. Actually, each time takes only 5 minutes or less than 10 minutes. And this one is the main advantage of our LTRO method, because we don't solve the equation by numerical method. Actually, we solve the equation by a stochastic method. And we can run several cases in the short time. So here, when we run the several cases, we can combine them and we can calculate the P10, P9, P50, and P90. And when we have this tree map, we can go to the opportunity identification. In the software, you can make some polygon, and the software can produce some information about those polygons. For example, the software can tell you what is the amount of mobile oil impress in that polygon, or what is the amount of stoic or oil at that polygon, or what is the average porosity, permeability, or what is the TVD at that location of the reservoir. So you can rank your target or infill location based on those information. When you rank your target, you can go to the prediction module and run the forecasting. Actually, our forecasting is based on the machine learning. Our LTRO is a combination of the physics and the stochastic method, but when we go to the forecasting, is based on the machine learning. That's why we call the Poseidon as a hybrid tools. And in the forecasting, we can produce a range of the oil production for you, as you can see at the bottom of the screen, or range of the EUR for each target. For example, what is the P10, P50, and P90 for each target? And this can be quite useful when you want to make a decision. For example, you can look at your low case. Is economic, for example, if we get the low case, or what is the difference between our P10 and P90? Sometimes the difference between the P10 and P90 is wide, and it became quite risky to drill that target. But for some target, P10 and P90 is quite close, and both of them are economical. And maybe that target is much better for drilling.
Bob, could I kindly ask you to wrap up the presentation, as we are kind of short with time? Really.
Okay. I have 2 more slides. Okay. I try to wrap it up. As I mentioned, for forecasting, we use machine learning. Our machine learning is powered by Python and TensorFlow. Also, we developed some in-house code, because some of the client doesn't like to pass the data to the third-party tools. That's why we can use our in-house code for machine learning. Okay. And as a last slide, I want to show you some field implementation of the Poseidon. Actually, here you can see 3 different field implementation of the Poseidon. The first one is in the North Sea. We use the Poseidon as a preliminary tool to study of this field. This field is the offshore field in the North Sea. The drilling of the well in the offshore is quite expensive. That's why they use the Poseidon as a preliminary tools for screening the target. And after that, they use the numerical simulator for fine-tuning of the drilling location and get more details, actually. The second application was in Oman, heavy oil located in the Oman. Actually, they use the Poseidon for this study. Later on, they done some sector modeling to validate the Poseidon. result, but when they went to the prediction and for drilling, they used purely Poseidon result. And all the results published in the SP, you can see the SP number in the left side of the screen. And the third application is in Romania. They use purely only Poseidon software for identifying the remaining oil target, and they drill the 3 wells, if I remember it correctly, and the result has been published in the conference that you can see in the left side of the screen. Also, they provide us some letter about the successful drilling of the wells. Yeah, that's all about the Poseidon. Thank you for your attention. And in the LEAP, we are thinking the future is today, and the future will be digital. Yeah, that's all. Thank you for your attention.
Okay, thank you. Hamid, I will just start the question session, if that's okay. Very
Absolutely.
good. Babak, thanks very much. Very comprehensive presentation. Clearly a comprehensive set of software, and I'm hoping that there will be many questions coming through on the chat box. I do have one question which I've prepared, which I'm going to hit now, and everyone on the call could indeed input their questions. I see one from Peter, and it says, "What does compliant mean here?" You might want to retype that one and make it a little bit more clear, Peter.
Okay. Actually, if I go here in our slide tag, actually we call it compliant mapping. Okay, first of all, here in our ROCM, we use the 2D maps, but we consider the heterogeneity at the well level. So one of our input in the log data, and sometimes your geological model is not consistent with your production data. So the map sometimes cannot match the saturation at the well level, or sometimes you cannot match your material balance. That's why we call it the remaining oil compliant mapping, actually.
Okay, thanks, Hamad. And this time I will remember to switch on my microphone. Good morning, everybody. As I was saying, but no one heard me, that was a very comprehensive presentation, comprehensive set of software. Many questions we could ask. I have included one in addition to Peter's question regarding compliant, and that is, Hamad, what would be the technical aspects of a field study which could limit the robustness of a Poseidon study as such? If you could answer that one very quickly. And we don't really have much time left for questions, but if there are any more from the audience, if you could just enter them, I will take one more after this. Hamad, can you answer that question?
Sorry? What
would be the technical aspects of a field study which could limit the robustness?
Okay. You know, the Poseidon has been designed for a mature field, and for running all of those modules, we need enough production data, and we should visualize or meet the water breakthrough at the well level. So I can say the main limitation of the Poseidon is if you want to run the Poseidon workflow. Okay, first of all, you need to have enough historical production data. And for some of your wells, you must meet the water breakthrough time at some of the wells, not all of them. By this way, we can find, okay, where is the water, and we can map it. But if all of your wells is dry, maybe the Poseidon is not a good software, a good tools to study your field. Or if you have a few wells, for example, 1 or 2 wells at the field, maybe the Poseidon is not a good software to study those type of field. But when you have several wells, you already meet the water breakthrough at the well level, so the Poseidon can be quite helpful actually.
Thanks, Hamid. I understand from that that robustness of the solution will increase as the well density increases in your field, roughly speaking. There is one further question from Peter: is uncertainty in production data addressed or accounted for? I suggest, though, that perhaps, Peter, if you could get back to Hamid on that separately, because we're pretty badly running out of time, and I see Hamid getting very nervous there on his little picture.
Yeah, thanks, Dave. Yeah, absolutely. I would suggest, Peter, if that's okay, if you could share your basically email address with us, I will put you in touch with Babak so that you can have your discussions with Babak like at a later point. I really apologize, but we're kind of running out of time here, so I would like to, if that's okay, we put Babak and Peter in touch at a later time. So Peter, please provide us with your email address, and I'll make sure that happens. And having said that, I guess we'll kind of hand the floor to Wesley for the next presentation. Thanks, Babak, for the presentation.
You're welcome, and thank you for this given opportunity. Thank you so much.
Wesley, floor is yours.
Okay, thanks, Hamid. You want to play the 1-minute video now? That's it.
Hi, I'm Matt, and I'm here today with iRPM Petrophysical Modelling. Hi, how are you doing?
Very good, thanks. Yeah.
Would you like to tell us a little bit about your company then?
So, innovative reservoir petrophysical modelling determines the hydrocarbon volumes from the 3D seismic, calibrates one of the oil wells and I blind test against the others. So it determines in-place volumes, recoverable volumes, and it's faster, cheaper, and more accurate than current methods.
Okay, great. And is there anything that you've got with you that you'd like to show us today?
They've got a little video here that I can show you. So I just press play, and you can see the plan view of the 3D predictions going down through the reservoir. And there's actually 3 different fields there: Iago, Wheatstone, and Pluto. So it's calibrated to one of the Wheatstone wells. Just as long as the seismic covers any of the fields, then I can predict outside of that well.
Fantastic. Thanks very much for your time today.
Thank you.
Okay, thank you very much, Hamid. So I'd like to start my presentation. Imagine drilling your oil wells and having no geological surprises, no dry well results, and predicting the field production for the next 5 to 10 years, all using your existing data. My name's Wesley Emery, and my company iRPM can do this for you now. Using the existing 3D seismic data, at least one well log data set, your entire subsurface field can be quantified and validated using the iRPM process. So to go through my presentation quickly, I'm going to try and get it done in about 8 minutes. So the table of contents, I'm going to discuss a bit about the background, current situation, the 3D deterministic modelling iRPM uses, the actual technology that I've developed. I'm going to show an example in the Wheatstone field on Northwest Shelf, Western Australia. I'm going to show the 3D in-place volume property and also the 4D produced production volume. Then I'm going to go into summary, conclusion, and be ready for some questions. So the background: historically, hydrocarbon volumes are determined using the gross rock volume, net reservoir to gross thickness, the average porosity, the average saturation, and an expansion constant determined from at least one discovery well. This should only be used as a quick look estimation. The global financial crisis could never be predicted using averages. Similarly, good reservoir quality will never be predicted using averages. So the current conditions. In too many major capital projects, the end of field hydrocarbon volumes are often outside the initial uncertainty range, and most are below the initial low case, as you can see from this diagram. Why is this? Petrophysical cutoffs and averages often overestimate net pay. This results in underestimating permeability, requiring perm scale factors of 3 to 5 times at best to material balance the field production. Too often the variation around the average value of the property is modelled without regard to the probability of the precise value. So the current situation, we have typically 5 to 10 exploration wells, and they typically cost anywhere between $20 and $100 million before financial investment decision is made. So we have our exploration program, appraisal program, and development program. As I said, 5 to 10 years it takes to go through this program. You might have 3 wells in the exploration program, maybe 4 in appraisal, and maybe 5 in the development program. But with this process, you can break away from the appraisal program altogether. You can actually potentially remove the entire program. You can reduce the time down to 5 to 10 years, and the cost savings can be hundreds of millions of dollars by not requiring the appraisal program. The deterministic modelling methods that I've developed increases accuracy, and it's validated with blind testing. The cost is reduced, requiring less appraisal wells and less processing time. The process uses science, physics, and mathematical relationships rather than conceptual stochastic models based on averages. Uses a deterministic approach calibrated to at least one exploration or discovery well. A robust 3D prediction is then determined, and it can be used with old or new seismic. The methodology, we calculate the reservoir properties constrained to and reference to the 3D seismic trace or impedance. We develop relationships for water, gas, oil, and residual hydrocarbon at the calibration well, and typically we use Gassman relationships to do this. Then we blind test the predictions with new or existing wells, and this validates the model. We populate into the 3D space with the predictions based upon the calibrated well. Then we use existing relationships of permeability and saturation, which are a function of the V-clay, porosity, and reservoir quality into the 3D model. So here's the example of Wheatstone. We've got the seismic in the top left corner there, and we've got 4 of the Wheatstone wells. So you can see the seismic. And on the right, we've got the 3D property V-clay and the porosity in the bottom left and the permeability. So this actually covers 3 different fields, although it's calibrated to the Wheatstone field here. It also covers the Iago field, which is in pressure communication. And it also starts to predict the start of the Pluto field, which is a neighbouring operating company. So we can determine the in-place volumes, and we can also determine the ultimate recoverable volumes by determining the residual flushed saturation that's left behind. Hamid, can you show that 20-second video now, please? So this is the same presentation, just physically showing you that the properties changing as it goes down through the reservoir in the plan view. So you can see all the seismic, polymer clay, porosity, and permeability properties being predicted in 3D, all constrained to the seismic. Okay, back to the presentation now. So how do we determine the 4D properties? I use a drainage saturation height function to capture the in-place volumes, and then I use an imbibition function, number 2 curve here, to capture the residual volumes. So In the 3D property prediction, I determine the properties with water-filled porosity. Then I go and put in the drainage function to fill the hydrocarbons and make sure that that matches what we see in the wells. And then I use the imbibition to capture the residual volumes after production. And all this can be calibrated to core data. So what does this look like in 3D space? The top right-hand corner, we have the impedance volume of the gas initially in place using the drainage function. And you can see the original free water level here. So we've got gas above there. And then on the bottom left, we have the original free water level moving up to the current free water level. And so in between there, that's where all the production has occurred. And it's simply a subtraction of the in-place impedance minus the residual impedance. And then you can start to identify all the flushed hydrocarbon and where the unflushed hydrocarbon occurs. So in summary, 3D deterministic petrophysical modelling will predict the petrophysical properties in 2 to 4 weeks from the seismic data. Predictions are validated and blind tested against existing petrophysical well results. All standard petrophysical properties, the volume of clay, porosity, permeability, saturation, etc. are determined, in addition to reservoir quality, static in-place volumes, and dynamic residual volumes. So that's the end of my presentation, and thank you for listening. Open for questions.
Okay. Well, hey, thanks very much indeed, Wesley. And as with the previous presentation, I will now open the floor for questions from the folks out there. I don't see any questions just as yet. So Wesley, I do have a pre-prepared question, which I'm...
I've lost your voice, David.
Thanks, Wesley. I have an annoying habit of forgetting to switch on my microphone. Hey, thanks very much, as I was saying, for your presentation.
Yep.
Indeed, the extension of nominally 3D or classically 1D petrophysics to full 4D representation of a reservoir. And to the folks out there, if you could please input any questions you may have, and I have just put one in there, Wesley. And that question is, what would you say were the key limiting factors which would enable use of your 3D, 4D technology?
Sorry, what are the key?
The key limiting factors or limiting technical aspects of your data sets which could limit the use of the technology.
Well, it'll be no surprise to you that the key limiting factor is the resolution and the quality of the seismic. So the relationships I've developed are determined from the log acoustic impedance and elastic impedance. And so those relationships are pretty accurate. They're very, very similar uncertainty to the standard petrophysics. And then I go and apply that to the seismic impedance in the 3D space. So that uncertainty is the greatest uncertainty in the process, which is actually trying to marry the seismic inversion product, which is the acoustic impedance, to match what you see in the well. So that's where the greatest uncertainty is, and also seismic resolution is typically 2 meters. And you can start to improve that resolution a little bit, but then you get more and more noise. So that's where the limitations are.
Okay, thanks very much. I don't see any questions coming yet from the floor. I'm going to give you another one then, Wesley. You quote the 10 to 20% uncertainty for the properties across your grid, and yeah. I'd ask some questions about the grid, but maybe later. But are there some of these properties which you would consider are typically more robust than others?
The porosity prediction is better than the volume of clay prediction. And you know that I think I didn't actually have a slide on that, but I have that available. But the porosity is more accurate than the volume of clay, but then all the petrophysical relationships that I use as a function of those two properties have the same uncertainty as you would in the log domain. But because you're using the porosity and V clay from the seismic, then those uncertainties propagate into the final petrophysical properties of perm and saturation and the height function. But so that's where some of the uncertainties are.
Thanks, Wesley, I understand. We have got two questions actually from the floor. Peter's already asked some, so I'm going to give the first dibs to Nur Ismail, who has asked, when you impose the Gassman equations to restrict your reservoir distribution, do you plan on applying new or other rock physics approximations to aid your interpretations or to reduce the uncertainties?
Well, as I mentioned in the presentation, I determined the fluid water-filled properties of the porosity into the 3D space, and I used the Gassman on the well data to calibrate the water-filled porosity from the well data to the seismic. So I do that for the gas, oil, and if there is residual volume. So once you've got the 3D space with water-filled porosity, then you put in the height function, as I mentioned, and then you can recalculate all the rock property calculations that we normally do in geomechanics and rock physics. So you can start to determine stress regimes and do all of the rock physics calculations from there.
Very good. I'll take Peter's question now. He was actually up front. So Peter asks, how is the uncertainty range in the modeling results shown in the software?
Well, you would cross-plot the the blind test well porosity and volume of clay against the predicted porosity and clay from the seismic at that particular well location. So you would calibrate against another well and then go and populate it into the 3D space and use that property at the blind test well and compare it to what the well is, the actual petrophysical well volume of clay and porosity. And you can do that as many times as you like. So at best, it's 10%. That's pretty much at the calibration well. But typically, it's something, the porosity uncertainty is something like 20%. But, essentially, it picks up where the sands occur, and it's really an uncertainty on what the porosity is in that sand. So it can identify where the clays are, where the sands are, and the uncertainty is the actual petrophysical property of porosity and clay in those areas. So you blind test against the other wells.
Great, Wesley, thanks. And last question actually coming from Emeric, and his question is, or her question, sorry, how do you differentiate fluids?
Good question. If you have a well that has a gas column, and ideally that's why you need an exploration or a discovery well, then you do your Gassman and determine what your water-filled porosity would be, and you apply that relationship where you've done the Gassman determination over the fluid interval that you see in the gas column in the 3D space. And so then if you also have an oil column, then you apply that. So there's going to be some uncertainty of exactly where that occurs, and you need to look at fault blocks and closures of the reservoir. But this technique you can start to apply in a general sense to the entire 3D space, and then you can start to see any differences, and then you can apply the different fluid levels and the different intervals of the Gassman process to the well, and then put that into the 3D space until you get a good match to existing wells.
Great, thanks very much, Wesley, and to everybody who's got who have put questions onto the chat box. Many thanks indeed for all of that. And I will now pass you back to Hamid, who I think will take over the session.
Thank you, Wesley and Dave. I wanted to take a moment to thank basically our audience for attending the webinar today, as well as our basically presenters. Thanks to Babak, Wesley, and Dave for hosting the Q&A session. Before letting everyone go, I would like to basically let the audience know that they're able to ask any questions from the folks today regarding their technologies through TechnologyCatalogue.com platform. You can just basically go to the respective technology page under the module Subsurface and submodule Reservoir Modeling, and you could basically access the technologies and ask your questions from the presenters. Also, you can drop us an email at info@technology.com, and we can definitely put you in touch with the presenters as well. Also, just wanted to, before finishing and letting everyone go, wanted to raise out another point that now with the coronavirus pandemic, perhaps webinars are a good way to stay connected. So please check our TechnologyCatalogue.com webinar page for our upcoming webinar, and we'll be happy to host you again at later weeks. Thank you very much, folks, and have a good rest of the day. Thank you.
Thanks, Hamid. Thanks, David.